Okay, so we have an article here called Thermal Energy is Not Temperature. And they capitalized all of the words in not, so that's important. The opening picture is a bowl of soup, and it says a bowl of soup is hot because its molecules have a lot of kinetic energy. So let's dive into the reading. Imagine that you and your little brother are sitting in the kitchen on a cool autumn day. There's a pot of soup on the stove, and both of you are hungry. You pour yourself a big bowl of soup, but your little brother can't eat that much, so you pour some into a small mug for him. When you go to taste the soup, however, you realize it's still too hot. You could wait for the soup to cool by itself, but you're hungry now, so you grab two identical ice cubes from the freezer. You drop one into the bowl of soup and one into the mug of soup. Once both ice cubes have melted, you take a spoonful of soup from the bowl. The temperature is perfect, warm and hearty, but not too hot. You infer that your brother's soup is the same temperature. Have some, you say. Your brother dips his spoon into the mug, takes a sip, and makes a face. Mine's cold, he says. At first, you think he's just complaining, but then you take a sip from his mug. It really is cold. What happened? Both the bowl of soup and the mug of soup started off at the same temperature, and you added identical ice cubes to each. So why did his mug get cold while your bowl stayed warm? Since the two containers of soup began at the same temperature, the molecules in the bowl of soup and the mug of soup started off with the same average kinetic energy. However, that doesn't mean they had the same thermal energy. Thermal energy is the total kinetic energy of the molecules of an object or material, and not the average kinetic energy. Each molecule in an object or sample adds its energy to the total kinetic energy. The bowl contains a lot more soup than the mug, and because the soup is made of molecules, more soup means more molecules. Each additional molecule contributes the kinetic energy of its movement to the total kinetic energy. As a result, your bowl of soup has much higher total kinetic energy, or thermal energy, than your brother's mug. Why is this important? Well, since the two ice cubes are identical, we know that the bowl of soup and the mug of soup each have to transfer the same amount of kinetic energy to the ice to melt it. In both cases, transferring that energy to the ice makes the soup cool down. However, in the case of the mug, this transfer of energy cools the soup much more because the mug doesn't have a very high total kinetic energy to begin with. The bowl has a much higher total kinetic energy because it contains a lot more molecules, each of which adds some energy to the total. Thanks to these extra molecules, the same transfer of kinetic energy has a smaller effect on the temperature of your bowl of soup than it does on your brother's mug. Let's say you put your brother's mug of soup in the microwave to heat it up again. Now it's very hot, much hotter than your bowl of soup. The average kinetic energy of the molecules in your brother's cup of soup is higher than the average kinetic energy of the molecules in your bowl of soup. What about the total kinetic energy or thermal energy? Is it possible that your bowl of soup could have a lower average kinetic energy or temperature, but a higher total kinetic energy, thermal energy? Yes, your bowl of soup probably has a higher total kinetic energy than your brother's mug of soup because it contains more molecules. All of those molecules contribute to its total kinetic energy. To calculate the total kinetic energy of something, add up the kinetic energy of all of its molecules. So even when something has a low average kinetic energy or temperature, and it isn't very warm, it can have a high total kinetic energy or thermal energy if it has a whole lot of molecules. Now imagine that you're waiting for your soup to cool down and you leave it on the counter while you go do your homework. Your homework is so interesting that you forget all about your soup and now it's cold. Actually, if you were to measure the temperature, you'd find that your soup is the same temperature as the air in the room. What is going on? If you think of your bowl of soup and the air in the room as two parts of the system, then the explanation goes like this. Your soup is hotter and the air is cooler. Since energy always transfers from warmer things to cooler things, the kinetic energy of the molecules in your soup is transferred to the molecules in the air as the molecules collide with each other. The system continues to change, transferring kinetic energy between the soup and the air until the soup and air reach the same temperature. That is, their molecules have the same average kinetic energy. The soup and the air are in a stable state of equilibrium. Your soup seems to have cooled down quite a bit, but you probably didn't notice any change in the temperature of the air. This is because there are many, many more air molecules than soup molecules. So the air has a much higher total kinetic energy or thermal energy than the soup. And you wouldn't need to transfer and you would need to transfer a lot more energy in order to change the air's average kinetic energy or temperature. Remember, thermal energy and temperature are not the same thing. So here we've got a caption or a picture with a caption. It says, the bowl of soup on the left is the same temperature as the mug of soup on the right because both are made up of molecules that are moving at about the same speed. So they have the same average kinetic energy or temperature. However, because the bowl of soup is made up of more molecules, it has a higher total kinetic energy or higher thermal energy.